Welcome back to the next lecture on drone systems and control. In the previous lecture, you have gone through the understanding of transient response in control systems. However, in this particular lecture, we will be talking about the Matlab demonstration of the particular topic on transient response. To start with, you have seen that there was an example or mass spring damper. There was a differential equation for that, and we know by this time that when we have a differential equation, if we take Laplace transform of both left side and right side and then take the ratio of Laplace transforms of output and input, we get the transfer function of the system, right. So, from differential equation we are getting the transfer function. In the case of second order system like mass spring damper, the transfer function is also a second order. What does that mean? It will have something, the power of s here will be the power will be 2, s square term will be there. How it is coming? It is coming from this particular term, the double derivative in the differential equation, right. So, this is the form of the transfer function for a second order system, where gain k is generally equal to omega n square. So, we have gone through all this term. What is omega n? Omega n is a natural frequency. This is in general the expression for that. It depends on the dynamic properties of the system, right. Now, there was another important thing called damping ratio. It measures how quickly the oscillations decay. If the system is not getting stabilized in a specified time, then these oscillations remaining in the system can be challenging to handle. So, damping ratio is a term which should be tuned properly for a system, right. This is the expression for damping ratio, right. Now, we have seen that omega n is responsible to control the speed of the system, while zeta shapes the smoothness and overshoot. Okay. So, we have seen how the responses look like with the standard second order system. In this particular lecture, we will see and we will try to code in Matlab and see that how things look when we simulate these particular things in Matlab. Okay. So, this is the time domain differential form. This is a standard transfer function form where this omega n square term is present in both numerator and denominator. Okay. This is the numerator which is having omega n square only and no s term. So, we can say that inherently this system does not have a 0. However, being a second order system, it has 2 poles, right. If we solve the equation s square plus 2 zeta omega n s plus omega n square, we will get 2 poles s1 comma 2, right. Okay. Now, we have seen that omega n is called natural frequency. This is the unit and it checks how fast the airframe or drone wants to oscillate if disturbed. Okay. So, omega n controls the speed in a different language. Okay. Zeta is the damping ratio. It checks about the oscillations. Tuning zeta can give different level of oscillations or no oscillation. So, the value of zeta is very important and k is a DC gain, right, if it is used. Okay. So, what are the poles? I have told here that there are 2 poles S1 and 2 if we solve the equation. So, the poles look like this, right. You see, when we have poles like minus zeta omega n plus omega n square root of zeta square minus 1, we can vary the value of zeta to check different performances. So, when the value of zeta is between 0 and 1, we tell that the system is under damped. Okay. What happens at that point of time? It will have a complex pair of root which will have sigma and j omega value, right. What happens here? If we have the under damped response, the response will be oscillatory and it will decay, right, because of the damping. If it is critically damped, that means zeta is equal to 1, then there will be 2 equal real poles, okay, and it will be a fastest non oscillatory response. However, if it is over damped, then we will have 2 distinct poles, right? So in that case, if zeta is greater than 1, then we have two distinct poles. One is minus zeta omega n plus this term, and another will be minus, right? So these are the poles for overdamped case. These are the poles for critical damped case, right? And these are the poles for underdamped scenario. Okay, fine. Now, how the damping ratio actually works in the system and how it governs the oscillatory behavior, we will check. So when we have underdamped system, or the zeta is between 0 and 1, we see that the response will be something like this blue curve, right? This one. When this at that point of time, the transient response metrics, which will be very much significant to decide, are rise time, peak time, overshoot, and settling time. So these metrics are performance metrics. If we want certain rise time or certain peak time, or we want to keep the overshoot in level which is desired for the entire system performance, or we need the system, underdamped system, to settle down in a certain point of time, varying zeta can give us, zeta and also omega n will give us different desirable performance metrics. Okay. When zeta is equal to 1, that means it is a critically damped system, right? So for that, what we get, the response will be something like this. Okay, you see that it is the fastest one among the other two, like all three scenarios, which settles down to the steady state value of 1 at the quickest possible time. Okay. So when zeta is equal to 1, the system does not oscillate. So this overshoot will not be there for this particular scenario or critical damping scenario. Okay, no peak or overshoot. Rise times becomes slower, and it doesn't mean much, because in this case we don't have the peak overshoot. So it gradually increases, the response gradually increases and settles down to the steady state value, and the response becomes monotonic exponential decay. Okay, fine. So when it is greater than 1, that point of time also the system does not oscillate, and we tell that this system is a overdamped system. So we are checking for 3 different values of the system. One is 0.4, which is underdamped scenario. Another one is 1, which is critically damped scenario, and the third one is a overdamped scenario where zeta value is equal to 2. Fine. Yeah. So when we check a typical response of a second order system with zeta value between 0 and 1, we have seen that we get a decayed oscillation in the system response. What do we mean by that? The response rises from some point, goes high till this point, which is called the maximum or peak overshoot over the steady state value. So this arrow, black arrow, shows what is the peak overshoot. The point or the time stamp at which the peak overshoot occurs is called peak time, TP. When the response rises from, say, 10% to 90%, that point of time we say 90% of what? The steady state value, that is 1. So this one is the steady state value, right? Okay. So from this point to this point, the time taken by the system is called the rise time, and the point of time when the response comes between a certain tolerance level, given by this dotted line, that particular time is called settling time. So, what is desirable in a system performance? We don't want higher overshoot, we want to keep it less. So, ideally if we do critical damping, then we don't have the this overshoot in the system. If we do over damped response, that means zeta is greater than 1, then also we will not get this overshoot, right. So, the ideal system performance will be having overshoot as minimum as possible, rise time should be less, then if the overshoot is not desirable, then there is no question of peak time also, and we also want the settling time to be as less as possible, so that the system responds faster and comes down to a steady state value as soon as possible. Okay. So, this was the brief outline of the idea in transient response chapter. We have 3 to 4 performance metrics like rise time, peak time, settling time and overshoot. We have gone through the basic idea, the formula, how to calculate it from the system response. If we have the value of zeta and omega n, then how to calculate rise time, peak time, overshoot and settling time. Those things we know. Now, we will go to see in Matlab demonstration that how we can write the code to get different system performances. Okay. Fine. Now, I will write for a system where we have zeta equal to say 0.4. Okay. We also need omega n, we are keeping it as 5. Okay. Now, we know that when we are going to specify a transfer function, we have to write it in terms of numerator and denominator, right. So, we have seen in the transfer function of second order system that the numerator will be omega n square. Okay. And what will be the denominator? The denominator will be, the first term is s square, so it is only 1, then the second term is 2 zeta omega n and s. So, the coefficient will be 2 zeta omega n, right, and the last term will be again omega n square, right. So, this is the denominator. Now, how do we define the system? We define the system in terms of a transfer function whose numerator is this particular variable and denominator is this variable. Okay. If we try to see that what will be the system, we see that it looks like this. Omega n is 5, so omega n square becomes 25, s square 2 into zeta into omega n. Okay. So, 2 into 5 into 0.4 becomes 4 and then again omega n square. Okay. So, now we know that what is going to be the system, what is going to be the transfer function, how it will look like. We have specified zeta, that is the damping ratio, we have specified omega n, which is the natural frequency, then we write the numerator and denominator of the transfer function appropriately as it should be for a second order system. Since we have zeta is 0.4, which is less than 1, we know that we are writing a transfer function for a under damped system. Okay. Fine. Now, we will see that if we give a step response, then how the response will look like. Okay. Yes. So, you see Since this is one underdamped system, we have certain peak overshoot here. So we have a concept of peak time, we will have rise time, we will have the settling time involved here. Okay. Now it will be better if we add a grid in the particular plot, so that we can see that how much more or less how much peak overshoot is coming. We can see that it is much a little bit higher than 1.2. So we can say that the overshoot is higher than 20% because the steady state value is 1. Okay. So this is the step response. It looks like one decade oscillation. Okay. And here we will change the value of zeta. Now it is a critical damping, sorry, it is under damped system where we have 0.4, right. If we make it say even less damping, then what will happen? Let's see. So you see, since this is the damping ratio, as we reduce it, we see that the overshoot is getting increased. Okay. If the overshoot increases and damping ratio is decreased, then what will happen? The rate of decay of the oscillation will also decrease. So we see more oscillations into the system, right. Fine. Now we make zeta to be around, say previously it was 0.4, we make it 0.8. How it changes? You see, now the peak overshoot has significantly reduced, right. So it might be nearly say 1% or something like this. Okay. Now if we do a critical damping, that means zeta becomes 1. How it looks like? Fine. Once it is a critical damping with damping ratio equal to 1, we see that the overshoot vanishes. Okay. If we make it 2, then what will happen? Then you see the system response again changes for an overdamped system. So it is a suggestion to the students that you take different values of zeta. That means it can be something like zeta 1 is say 0.2, right. Then you can take another zeta that is say 0.8. The third one you can take zeta equal to 1, and the fourth one which is more than 1, right. If you do this keeping the omega n same, then you will see that the system response will change accordingly with the values of zeta. Okay. You can then understand it very clearly that when you are increasing the value of zeta, there is a trend in the transient response that the overshoot is coming down, and the rate of decay of the oscillation in the decay oscillation response is coming down in a quicker fashion as we increase zeta. When the value of zeta reaches to 1, we do not see the system having overshoot at all. If we increase the zeta from critical damping to over damping, that means higher than 1, then also there is no overshoot in the system, but there is a difference in a critical damping scenario and over damping scenario. Okay. So I request the students to plot this response accordingly and tally that how things are changing with different damping ratio. Okay. So this is about the Matlab demonstration of transient response. What we can see, we observed it in this particular lecture. We have gone through the basic brush up of the very fundamental concept of damping ratio and natural frequency, and we check how changing damping ratio actually changes the system response. So thank you for attending this lecture. In the next lecture we will go through understanding the concepts of state space, eigenvalues, etc. Okay, thank you.